Okay, in this video what I want to do is basically describe the theory of instant centers for dealing with rigid body kinematics from Chapter 16 of Hibbler's textbook. I've already talked about it briefly in class, and so let's remind ourselves of the idea of instant centers that I've already talked about. If a body has a permanent center, meaning this body, and this is a planar body, is pinned to ground right there, then this point on this body cannot move. It has V equals 0, which is one of the characteristics of a permanent center and an instant center. Let me bring up my zooming device and zoom in a little bit. Give me a moment. Okay, and so we'll zoom in a bit. That way I don't have to write quite so large. And this body is then free to rotate about that instant center. If that's true, we can say a lot about the velocities on this body when we know that that's a point that has zero velocity and pure rotations going on. So the velocity of this point on this body would be velocity of point A, and I can draw an RA vector from the instant center to A, and I know that for pure rotation on a rigid body that the velocity of point A must be perpendicular to that radius vector. And I know that its magnitude is the size of RA times omega of the body. And so we're just going to call that an omega. Oops, hit the page. Let's bring that back in view. I also then could know that the velocity of this point on the body, we'll call that point B. And here is an RB. The velocity of this at this point must be perpendicular to the radius vector, and it has magnitude this R times omega. So VB is equal to the size of RB times omega of the entire body, and bodies have omegas, not points. And so we could talk about this point over here, which has an RC, and if I made the claim that its velocity was in that direction because of what we understand about velocities on rigid bodies that are pivoting about a fixed point, we'd have to say no, can't be true, because it's not perpendicular to the radius vector. Now let's use this picture as a clue on how to find instant centers. Let's say we didn't know what point this body was rotating about, but we knew this velocity direction at point A and this velocity direction at point B. What we could do to find the instant center is simply realize that perpendicular line thing that's got to happen, and realize that there is a line that points to A, and that line is perpendicular to VA, and I could draw that line and bring it on back and claim that the instant center must be on that line. And then for this point at B, I say if that velocity is true, then I can draw a line through B perpendicular to the velocity and say that the instant center must be on this perpendicular line passing through point B perpendicular to the velocity at point B. And lo and behold, the instant center has to be at the intersection of those two lines. If this one were true, it would tell me that the instant center would have to be somewhere on that line, and it would be inconsistent with the other two, so I'm going to claim that that one is in fact false. So I can find instant centers if I know the velocity direction at 2 points on the body. So I have a body, and I know that the velocity at this point is that direction. That's velocity of A. Here's point A, and I know the velocity at this point is in this direction, and that is point B. I'm not going to make any claims for the magnitudes being right, with the directions I claim are correct. And if that's true, then I can find the instant center of this body by drawing a line perpendicular to that velocity and extend it out as necessary, and at point B, drawing a line through point B perpendicular and it would appear that my instant center ended up being really, really close to A, but that's okay. It's the intersection of those two lines. That'd be the instant center of this body. For bodies that are moving through space, if we know two velocity directions, we can use intersecting lines to find the instant center. An application then is, once we know where the instant center is, we can use V equal R omega to find velocities everywhere. If this is the instant center, I know that the velocity at this point has to be perpendicular to that line, and its magnitude would have to equal to R omega. We can find the velocity anywhere on that body. Okay, an interesting simple problem that can be solved with instant centers is the ladder problem. So I'm going to draw a building and the ground and put a few windows on the building, and I'm going to prop a ladder up against this building. Okay, but unfortunately this ladder is going to begin to slide. Okay, and this point A on the ladder, and I have a point B on the ladder. As A starts to head downward, B is going to head to the right, and if I happen to know VA, an interesting question is, what is VB? Or vice versa. Typical instant center problems will proceed. First of all, the instant centers only solve velocity problems. They don't solve acceleration problems. We'll talk about that a little bit later and talk about why, but they're very good at solving velocity problems if the instant center is easy to find. And so the instant center problem usually flows with find the instant centers that matter and then write V equal R omega equations over and over and over again. This one is going to end up having us find one instant center and writing two V equal R omega equations. Let's see how it proceeds. I know that the velocity at point A is vertical. Therefore, I'm going to draw a line perpendicular to the velocity, and so I'm going to put, that's a right angle. I know the velocity at B is horizontal. Therefore, I'm going to draw a line through B, perpendicular to the velocity at B, and right there is the intersection of those two velocity perpendiculars is the instant center of this body. Which body? The ladder. Now, that point isn't on the ladder, but I'm going to claim the point is sort of on the ladder. And what I'm going to do is make it look like I've got a big plate, a big slab, which includes the instant center and the ladder and all points in between. And right now, the ladder behaves as if it's this edge on this plate, and this whole plate is rotating about that point. If there were a plate of this shape with that edge, the direction of the velocity at A would in fact be straight down, and on this big plate pinned right there, the velocity at B would have to be perpendicular to that edge, and so our instant center is consistent. And if we know VA, then we could say that VA is equal to RA omega A, where RA is the radius of the short edge that goes from the instant center to A. And maybe we would only even want to write it R of A with respect to the instant center. So we're measuring the distance between the instant center and A. And this omega A would infer maybe the wrong idea, like A has an omega and B has an omega. This is the omega of the body containing points A and B. So let's call it omega AB. So if I know VA, and if I can compute through trig or whatever this R value, and I'll always have to do trig to get R values, they're not going to be secret, then I can solve for omega AB. I know the rotational speed, omega, of this entire body, which right now contains the ladder. I said one instant center and two V equal R omega equations. The next V equal R omega equation will be VB is equal to R of B measured from the instant center times that same omega of the body, omega AB. I know omega AB. I'll use trig or whatever to get the R, and then I'll be able to solve for the velocity of B. Now, these, and if I knew a number for A and I knew numbers for all of this, I would have a number for B. I would know its velocity. Now the instant center for the ladder is located right here, right now, but as the ladder slides down the building, by the time the ladder gets, say, to here, that's a totally different position. Where is the instant center of the ladder when it reaches that point? And the answer is it still has a vertical velocity that way, it still has a horizontal velocity there. So through the new point A and the new point B, I will sketch in lines perpendicular to the velocity through the point, perpendicular to the velocity through the point. The instant center of the ladder body, when at a later time, has moved to here. Instant centers move as the body moves, and so we have to make sure at each position that we're interested in solving the problem using an instant center method, we have to be able to find the instant center. Let's look at a slightly more complicated version of the ladder in a building. And the more complicated version is the building is on a slope. And so again, we'll draw some windows and make it look like a spooky little building. And we have a ladder on here, and this ladder is going almost to the top of the building. Okay, and so here is point A, here is point B, and this is the ground, and the ladder is in fact sliding down with a velocity of A, and it is sliding down parallel to the slope with a velocity of B. We can find the instant center of the ladder because we know two velocity directions on the ladder, and so since this velocity direction is vertical, we're going to draw a horizontal line through point A, perpendicular, and then we're going to draw a line through point B that is perpendicular to the velocity of B, so perpendicular to that ground line. We'll sketch that line in. Where those two lines intersect would represent the instant center of the body containing points A and B, which is the ladder. To make the instant center appear connected to the ladder, we will sketch that in and say that's one big solid plate, and the ladder right now is attached to that edge of that big solid plate. And this time, let's presume I know the velocity of B. If I know the velocity of B, I can say that the velocity of B is equal to the radius from B, starting at the instant center, times omega of the body containing point B, which is omega AB, the body containing points A and B. If we know the velocity of B, and through trig we learn that distance, which would be here, or B with respect to the instant center, then we'll be able to calculate one equation, one unknown, omega AB. And the way these problems always range is, once you've found the instant center, start where you know the most. Let's assume I know the velocity of A. Start there knowing that velocity and find the omega of this body. Then move on, knowing the omega of the body, go find the velocity of B. Ladder problems are fairly short and simple once you have the instant center. So if I know the velocity of B is a number, I'll start here with the equation velocity of B equal RB omega. Knowing velocity in R, I get omega. Now that I know this omega for this body, and it must be rotating this way according to the sense of that velocity, I know omega AB equals a number at this point. Now, knowing the omega of this body, I can go find the velocity of point A by saying the velocity of point A is this radius of A with respect to the instant center. That would be this radius, R of A with respect to the instant center, and times the omega of the body containing A and B. I know the omega. I do the hard trig necessary to get R, this R, and then I can calculate this velocity. That's what I wanted, and that problem is over. Let's see. Let's look at another problem. and it's just mildly more complicated. And this one is called a slider crank mechanism. And what I have is a link that's pinned to ground. That link has a pin joint or connection, a hinge connection between a different link. And that link has a hinge connection to that block. And that block slides on ground and can only slide left-right. It can't move up-down, and it can't rotate. And we typically call the ground links 1 everywhere in these kind of machines. Then I'd have link 2 and link 3, and the block is link 4. So this is called a 4-bar mechanism, having 4 links if you count the ground, and we usually do. That's the convention. Alright, so, and this particular slider crank is set up kind of easy in that this line of sliding goes back through that hinge joint point. And so, let's talk about how an instant center problem might proceed. Let's assume I've got a motor on link 2, and I know this omega. Now, to know that omega, I could call that omega of body 2, okay, or we might have points A, the pin, B, the pin, and C, the pin. And so I could also call this omega of the body that contains points A and B. So I could call it omega AB. Okay, again, omegas apply to bodies, not to points. Let's say that I know omega AB. If that's true, again, we want to find instant centers and start where we know the most. So first of all, the instant center of link 2, or link AB, is this grounded pin joint. If a body has a grounded pin joint, then its instant center is easy to find, and using that as the instant center of body 2, I can then say that the velocity of point B from point of view of link 2 is equal to R of B relative to A, or the vector that goes to B starting at A. So RB relative to A times omega AB. And if I know that because it's given, and I know that because I know enough geometry that I can measure it or I can calculate it, I'm always going to have to trig out the geometry as necessary, then I can solve for the velocity of B, and that will become a known thing. Okay? Then I proceed from where I know stuff to the point where I've learned stuff. And what I've learned is the velocity of B. Now, B is a point on 2 different bodies. B is clearly on body 2, but B is also on body 3 and moves with body 3. And I'd like to know the instant center of body 3 now. Body 3 is not pinned to ground anywhere, but I do know that point B must move on a circle governed by this radius based on link 2. And therefore I know that the velocity must be tangent to that circle. And so if omega 2 is in the direction shown, then the velocity of B, v sub B, must be perpendicular to that R vector right there. Okay, I didn't draw it terribly perpendicular looking, but it must be perpendicular. Now, it sort of looks like this vector is parallel to that line, but it's not, and it really doesn't look terribly parallel anyway. So here's the velocity of B, a vector, and I know it from the point of view of link AB, but it's also the velocity of point B on link 3. And so knowing a little bit about what's happening on link 3 is going to let me know more about what's happening on link 3, because to find the instant center of link 3, or link BC, I will claim that I'm just extending this line on out. Now, what I'm really doing, since this is perpendicular, this velocity is perpendicular to that line, I'm just drawing the other piece of the perpendicular line. I'm drawing a line perpendicular to that velocity because that's needed to find the instant center. Then I know that this velocity, because of the sliding which is horizontal, I know that the velocity of point C has to be in the horizontal direction, and point C is also on body 3, so I'm going to draw a line through point C perpendicular to its velocity vector, And since I have 2 points on a body, B and C are both on body 3, I have 2 velocity directions on that body. I've drawn 2 perpendicular lines, and I've found the instant center of body 3, or body BC. And to indicate that this instant center is on that link, I'm going to shade that in and make it look like a solid plate. And the link that I care about, BC, is one edge of this 3-edge solid plate, which right now behaves as if it's pinned to ground. Okay? And if this is the instant center, then the velocity of B must be perpendicular to that line. I said it is. The velocity of C must be perpendicular to that line, if that's the instant center, and it is. So, found the instant center of link 2. Use the omega that was given to solve for the velocity. Now I know this velocity, which is also on link 3, so let's write that the velocity of B is also this RB compared to IC of this IC. So I'm just going to call that an RB on this body times omega. We'll use the V equal R omega equation over and over again, but I need to identify the omega. I could call it omega 3 for body 3, or I could call it omega BC because the body containing points B and C is body 3. At this point, I know the velocity from the previous step. Okay, and I know the R because I can always trig that out somehow. That means I can solve for that omega BC. Now I need to take another step forward using V equal R omega, and what I've just learned is omega BC of this body is known. I need to get the direction of omega BC just by looking at the picture carefully. Since this one started in this direction, VB must be up and to the left. If VB is up and to the left, this omega has to curl this way. These equations give me the magnitudes. I've got to look at the picture and determine the directions of the omegas. Now, what I'm going to do is use this omega, which is now known, to find the velocity of point C. And I just noticed, because I'm now paying attention to directions, velocity of point C has to point that way. That doesn't change anything we've done so far, but point C with this omega is going to be moving to the left. So now I'm on this body. I know the omega, but I don't know the velocity of C. So I'm going to say V equal R omega again. Velocity of C is equal to an RC omega BC. But I just found omega BC in the previous step. So now that's known. This RC is the one that I'm interested in. I want to know that magnitude, and knowing these two quantities, one equation, one unknown, lets me then solve for the velocity of C, and I'm done. So I used 3 V equal R omega equations to travel from known omega to known V, from known V to known omega, from known omega to known V, and the problem is over. Multiple V equal R omega equations and multiple instant centers. Now, very quick, we haven't done it yet, but block C, the block holding point C is a slider. What is the instant center of a body that moves on a straight line? Well, a body that moves on a straight line could be treated this way. Imagine I have a block, and that block is attached to a link, and this is welded to it, and so this is free to pivot. What path does the center of that block follow? It follows a arc centered here. This block does not follow a straight line. What if I scratch out that pin joint and I extend this link further down? Okay, put it where you can see it. What happens to the path if I make this long line longer? What happens to the path of this block? It follows an arc that is larger radius, therefore more shallow. Now, the arc that's being followed is of radius that's not a straight line either. What if I move this pin joint and extend this link down to infinity and beyond, as what his name would say. Okay, I increase the length of this thing to infinite. What is the radius of the arc that this block travels on? The radius is infinity. What shape is an arc of an infinite radius? A perfect straight line. So anything sliding on a perfect straight line, like this slider, can be said to have an instant center passing through the point perpendicular to the line of sliding, perpendicular to that velocity, okay, out at infinity. We'll hardly ever need to know that, but it's an interesting thing. So even bodies moving in straight lines can be said to have instant centers. They're just an infinite distance away, perpendicular to that velocity line. Okay, let's look at let me find from my earlier attempt at this video, which had no sound. Let's talk about a 4-bar mechanism. Okay, 4-bar mechanism is a link pinned to ground and another link pinned to ground and a connecting link with pin joints there and there. And so if I call the ground link 1 everywhere, then this might be link 2, link 3, and link 4. And what's typically given in a problem with a machine like this called a 4-bar mechanism, which is used in a lot of different places to give interesting motion using only one motor, quite often we know omega of one link, and we would like to know the omega of the final link on the other side. We could call this omega 2. We'll call this one omega 4 because it's on body 4. And so how would we proceed then to solve this problem using instant centers? Okay, I'm first of all going to label some points, and I'm going to call this one A0 and A, and B0 and B. Now, I'm going to do the instant center the easy way first, by simply taking this line and extending it out. And then I'm going to take this line and simply extend it out, and I'm going to claim that this point is the instant center of body 3. And I'll shade in the triangle as I usually do, just to help me visualize that this edge of this plate, which is pinned to ground right here, okay, right now is my body 3 connected by points A and B. That'd be the instant center of body 3. So let me call it IC3. Might be a nice name for it. Now this point A0 is a fixed center for a particular body, body 2. So I might call this point, which is labeled A0, I might also call it IC of body 2, moving body 2. How do I solve this problem? Knowing the instant center of body 2 and omega 2 is given, then I'll start where I know stuff and write V equal R omega. And I'm going to write velocity of point A, which is on body 2, is equal to some R times some omega. What omega? Omega of body 2. That's the body I'm focusing on right now, and I know omega 2. And let's call this R of A with respect to A0, or it is also R of A with respect to the instant center of body 2, IC2, because those are the same points. Knowing omega 2, which was given, I always have to be able to do the trig to figure out what that R is. Then I have one equation, only one unknown. I can solve for the velocity of point A. Now, the velocity of point A is going to be perpendicular to this line from the instant center of this body to point A. That's going to be the velocity of point A, and I know its magnitude from the V equal R omega equation. Now, point A is on two different bodies. It has to have the same velocity on the two different bodies, but it is on two different bodies. It's on body 2, but it's also on body 3. Okay, knowing the velocity of A from body 2, I can now say the velocity of A is also equal to an R omega combo, but this will be an R of A with respect to instant center of body 3. Then this has to be omega of the same body, body 3. Okay, now why did I say I can find this instant center? Simply by extending that line and extending that line, because the velocity of A must be perpendicular to this line. The instant center of body 3 must be on a line which is perpendicular to velocity of A. So I've got double perpendiculars, which means just extend that line. In addition, point B on this link will have to have a velocity when it's all said and done that's perpendicular to that line, because point B on this body has to travel in a circle and it'll be tangent to that circle. Now, the instant center of body 3 must be on a line passing through B and perpendicular to B this way. So this line is perpendicular to the velocity. Double perpendiculars simply say extend this line out to find the instant center. Now, so far, all I found is the velocity of A, and I've written the equation to use the velocity of A, which I just found from here, to use the velocity of A to find the omega of body 3. So I know the velocity of A from here. It came from the previous step. I can certainly trig out the radius somehow, and I will solve for omega 3. One equation, one unknown. At this point, I know the value of omega 3. I know its magnitude. I want to come up here and draw it in, but I want to get it in the right direction. Since VA heads up, this body must be rotating in that direction with an amount omega 3. Now that I know omega 3 for this body, I can proceed on to the next unknown on that body, and that would be point B. I don't know the velocity of point B, but I'm going to find it by writing what equation? Guess what? V equal R omega. And so the velocity of B will be an R of B with respect to instant center of body 3 times omega 3. Oops, that's a 3. I just learned omega 3 from the previous step. It's known. I can always do the trig and find out the magnitude of that vector R of B with respect to instant center 3. I know that R. The only unknown is the velocity of B, and so I solve for the velocity of B. It's now known from the one equation, one unknown problem. Now, I just solved for the velocity of B from the point of view of body 3, but that's also the velocity of B on body 4, and so now I'll turn to body 4 and start where I know something, this velocity, and work toward that omega by writing what equation? Well, of course, V equal R omega. So velocity of point B, which is known, I just solved for it, is equal to a different R omega pair, because I've changed bodies. Okay, this is the instant center of body 4, and so I'm going to have a vector that goes from the instant center to point B, and I'm going to call that R of B with respect to B0 is its current label for this vector right there, but that's also equal to R of B with respect to the instant center of body 4, where this link is body 4, because that's a grounded pin joint. That makes it not only the instant center of body 4, but it makes it the permanent center of body 4. And so using this equation, I'll fill in that this is an omega 4, and this is R of B with respect to B0 is a nice way to write it. It's that R. And I just solved for this, let's see, I just solved for the velocity of B. It was from the point of view of body 3, but that's still the velocity of B. And so this is known from the previous step. I can always trig out the r's, which means the only unknown is omega 4. This is a one equation, one unknown problem, and I can solve for omega 4 looking at the direction of the velocity of B, which came from that omega, so it heads that way. Then omega 4 must head that way, and I get its magnitude out of this equation. I had to find really 3 instant centers, but only one of them was hard. That's a permanent center, that's easy. That's a permanent center, that's easy. The only interesting instant center is up here. Again, for any 4 bar, just extend the 2 grounded links as a straight line, find the intersection. That's the instant center of the 4 bar. Start where you know the most and write as many V equal R omega equations as it takes to finally get to where you want to go within the problem. Let's see, just one other, maybe an interesting 4 bar. I might have this link there. I've got to think about this to get this about right. And that link is there, and this link is here. And let's get that to where you can see it. Pin joint, pin joint, pin joint, pin joint, or a hinge. Okay, and so maybe I know this omega, and I want to work my way to that omega, which probably is going to be in this direction, just looking at that picture. All right, so first of all, where is the instant center? If this is body 2, 3, and body 4, where's the instant center of body 3? And what I said to do is we extend that line out, and we extend that line out. Do they intersect? Yes, because I'm going to extend this one the other way. And where these 2 lines intersect by extending this link and extending this link, where those 2 lines intersect is the grounded instant center of body 3. I'll shade it in, and right now this link behaves as if it's pinned to ground right here. And so from the point of view of the short link 2 and omega, I could find VA, let's call that point A, with a V equal R omega. Knowing VA, that it's also ground on this big link, I could say I could find omega of body 3 from VA is equal to big R times omega 3. I could solve for omega 3. Knowing omega 3, I can solve for the velocity of this point on body 3 by saying VB, because that's point B, is equal to this R times the omega that I've previously solved for. Knowing the velocity of B, and that I'm on this link right here, and there's my instant center, little r times that omega 4. One equation, one unknown. Omega 4 is the unknown. Solve for that. Okay, I just wanted to draw this machine in this funny configuration to show you that the instant center is found the same way and located right there. That would be a 4 bar. A simpler kind of problem. Hang on 1 second, my virus system is telling me something. Okay, I'm just going to give that an okay. I don't think you were able to see it. Let's look at another very common system for finding instant center, or using instant centers to say something about the problem. And that is a wheel rolling on the ground. There's my wheel. There's my ground. The point of contact between the wheel and the ground is right there. And this point of contact is a no slip. Okay, no slip contact in this case, no sliding between these two. Anytime we have 2 bodies touching with no slip, that means they share the same velocity at the point of contact. What's the velocity of the ground at the point of the contact? Velocity of ground everywhere is 0. If the velocity of the ground is 0 at the point of contact and there's no slip, then the velocity of this point on the wheel must also be 0. Otherwise it would be slipping. And so, therefore, this is the instant center for the wheel. A wheel rolling on ground without slipping, the instant center is at the contact point. Now, what's the key definition of instant center? A place on the body where the velocity right now is 0. And obviously, as this wheel rolls and travels, the instant center will move along with it. So it's not a permanent center, it's just an instant center. But now that I know the instant center of the wheel, I can say several things. Let's go to the center of the wheel, which is not the instant center of the wheel. And let's say that this wheel has some omega in that direction of some known amount. If I know the omega of the wheel, then I can form an R vector. Let's call this C for the center of the wheel. And I can say that there is an R of C with respect to the instant center. Of course, that is just R for the wheel if it's a perfect circle. And I can say that the velocity of this point C is V. C is equal to the radius of the wheel times the omega of the wheel, V equal R omega. Now the question is, what's the velocity up here? Well, here's the instant center. The velocity is going to be in that direction, and since it's twice as far away from the instant center, this velocity will be twice as big as that velocity. Maybe I'll call this point D, and the velocity of point D is equal to 2r times omega. Now, conceptually, we can find the velocity of any point on the wheel right now. What's the velocity of this point on the wheel having that omega? It's going to be V equal R omega. Let's call this point E. So, velocity of point E is equal to an R E omega, where that would be R E measured from the instant center of the body. That tells me that point must have a velocity in that direction and a medium-sized magnitude. What's the velocity of that point? Right there. I draw my straight line to the instant center, draw a perpendicular line, kind of small. This point must have a velocity which is largely in the down direction and a little bit to the left direction. What's the velocity of this point? Straight over here. It's going to be perpendicular to that line, up at 45 degrees, V equal this R times omega. If I want to know the velocity of that point on the wheel, I draw a line, draw a perpendicular, and I can find the velocity of that point on the wheel using our magic equation V equal R omega. So, instant centers work for wheels that don't slip. So, that's the theory of instant centers, and I'm going to stop this video and then I'm going to look at a couple of examples using the idea of instant centers.